Thank you.
No problem. Okay, so let me go back to the beginning here. So as I was saying, this is the RL. The RL resistor is right here.
Claudio, before you start, I believe you can give us permission to record from our PC.
Maybe, but I mean, I don't think it'll make a difference, right? You'll have access to it on the
It
drive.
will be much easier for you. That's why I'm saying it.
I'm okay with this here.
Okay,
It's
perfect.
not a problem. Okay, so this guy here is RL. So to get the RL value, what I'm going to need is I'm going to need the voltage here. And what is the voltage here? Well, it's the voltage across EO, which is this given value here. So 12 volts. So I'm just going to write it down. The more I write down on the schematic, the less questions you'll have. It'll be more straightforward instead of shuffling to see what's what. So 12 volts right there. The current that's going into this branch here, also a given value, 15 milliamp. Okay, so with those, I can get the resistance. So here, RL. I'm going to take the EO, and I'm going to divide by the IL, two given values. Okay? So the EO is 12 volts, and I'm going to divide by 15 milliamp. Okay, so 12 divided by 15 shift milli will give us 800 ohm. Okay, so what I had said yesterday is, I'm just going to shift this over a little bit. Calculated and used is not necessarily the same thing, right? Do you remember what the denominations were in terms of resistance or resistors in our kit? We had a 220, we had a 4. I can write those down again. Actually, here I'm going to write them up here. So we had a 220 ohm resistor available to us. We had a 470 ohm resistor. Then we had a 1K. And then we had a 2.7K. And we had a 4.7K. And those are the only ones we're going to need for this exercise here. Okay? There are a few others, but amongst these, which one would we choose? Well, we're at 800 ohm. The thing with increasing resistance that you have to understand is if you increase resistance, you're decreasing amperage, which is not what we want necessarily. This is not a fuse, okay? It's not to protect. It's you want to build a circuit that has enough current to supply the load. So 800 ohm, so we're going to use a 470 ohm resistor. Okay. So I don't know if you noticed, but did we use this anywhere in our calculations?
You use what anywhere in the calculations?
This RL value. This force. We haven't in theory, but when we assemble the circuit here, the assembled circuit will have that RL resistor here. Okay, so for our calculations, we don't actually need the RL. The RB is a different story. The RB, which is on the next page. Okay, so if you're looking for RB, this guy here, now as I was telling Massimo before, this RB basically is to make your life a little simpler. Remove all of the other semiconductors, put the resistor value in with the amount of current that you need here, the given amount of current. And it's just basically to decide how much current and voltage is going through these diodes to choose the proper diode, okay, from our chart. So let's finish off with RB. So the voltage at RB, okay, we're not looking up here. Here we're looking at EO for RL, okay, which was 12 volts. But now we're looking at this circuit here on the next page. We don't have EO here. The voltage we have here, just so it rings a bell, right? We have a waveform that looks like this, right? So we have two positive peaks. This peak here is what we're using, right? This value here, the peak value. So here for RB, what we're going to do is we don't have E peak yet, so we're going to take E effective, and we're going to multiply by the square root of 2, just so it's nice and simple. And we multiply by 1.414. and then we're going to divide by IL. Okay. Let me know if you have an issue with that, please. So all we're doing is, if you actually, maybe I'll just clarify a few things. If I put this in brackets, maybe
Yeah.
a bit more sense, okay? And I'll space it out a little bit. So E effective multiplied by 1.414 will give us E peak, and then divided by IL to get the resistor value that we want right over here. Okay? Remember, we have IL. So if we plug in the values here, E effective, this one here was 20 volts. We're looking at 20 volts. We're going to multiply by 1.414, which, just to remind you, is the square root of 2. And then we're going to divide by IL, and IL is 15 milliamp. So if we do the math, 20 multiplied by the square root of 2 divided by 15 milli. So 1.88. So do 1.886 kilo ohm. Okay. So in our kit, we're going to choose again, 1.8. We're looking at 4.7 is too big, 2.7 is too big, 1K, 1K. This one is going to be important. It's going to be important because we have to use it here. When we get to IR here, we're going to have to use the RB value. And you have to use the RB value from the kit, okay, which is the 1K.
Hey, Claudio.
Yes.
So why is it that, okay, so I get how we got to the 1.886K ohm. That's cool. But why do we have to use this, like the smaller one as opposed to a larger one? Like, why are we using a 1K instead of a 2.7K?
Okay, so what happens if you increase resistance is that you decrease current,
Right? Yeah, okay.
which is not what we want to do here, because we're not here to protect the circuit like a fuse, right? What we're here to do is build a circuit that has enough current to supply the load. So if we increase resistance, we decrease the current. If we decrease the current, we're going to have less than what we need in order for us to charge the load.
Okay.
Okay? So if we reduce the resistance, we increase the current. So we need minimum 15 milliamps on our load.
Oh, okay. All right. Okay.
Okay?
Yeah. Okay.
It'll be a little bit clearer in terms of when we get to RB and when we get here I average, what the effect is on the current as well. So if this was a 1.8, okay, 1.8 is what we got here. And if we were to use 2.7, if we use 2.7 here, you'd have considerably less current.
Yeah.
You need
Okay.
a certain amount of current for the load to be charged.
Yeah. Okay. I see. Yeah. All right.
All right, so we're okay with this page here, 471K. We'll move on to the next page. Let me know if I'm going too quick. All right, so ER peak, well, we just did that on the previous page, or we started doing it. So E effective multiplied by the square root of 2, or 1.414. And if you multiply it out, it'll give us 28.28 volts. What does PIV stand for? Peak inverse voltage. So it's basically peak voltage. So the peak voltage, 28.28 volts. And that's basically when the current's going through and a diode is reverse biased, what is the maximum that it can block? Okay, and then eventually we're going to choose a PIV with PIV safe or merge them together and then go to our charts and compare it to VRRM. ER average is E peak multiplied by 0.636. So our E peak, 28.28, we're going to multiply by 0.636, 28.28, multiplied by 0.636, 17.986, 17.986 volts, and include the DC. Okay, so now here, since I'm looking for I, remember Eric,
Yeah.
not Schultz, the pyramid, triangle. Okay, so if I'm looking for I cover the I, I'm left with E over R. Okay, so E over R. But which E do I use? Well, it depends on which I am asking for. Since I want I average, I'm going to use E average. Okay, so I'm going to put in the 17.986 volts DC divided by 1,000 is going to give me 17.986 milliamps DC. Are we okay with that so far? Please let me know if you're not. ID average. ID average was IR average divided by 2 because the diodes in this circuit will get current only for half a cycle. So the positive half will go through this diode, the resistor, and this diode. The negative half will go through the other two diodes, but the resistor again. So it's going to go through the diodes half as frequent as the resistor. So I'm going to take the 17.986 volts DC, milliamps DC, and I'm going to divide by 2, which will give me 8.993.
Oh, actually, just going back for a second to the
Yep.
previous one. It's 17.98. What's that? Like BMAD. Wait, like the unit. That's the word. What's that unit at the end?
This is voltage. Up here?
No,
Yeah,
it's
no, to the right, to the right.
milliamps DC.
Oh,
Sorry.
that's just milliamp. Oh, okay, that's just milliamps. All right,
Milliamps
okay.
DC, yeah.
Okay, all right.
I'm trying to avoid writing. Here I wrote it down to show you the RB, but I'm going to type out the rest because
Okay, milliamps DC.
unless it's
All right.
really big, and I could make it a little bit larger, it's kind of hard to write. Well, give a pain. So ID average safe. Look, this is ID average. This is ID average safe. The difference is the safety factor. So we're going to take the ID average, which we figured out here, 8.993, multiply by the safety factor. In this case here, the safety factor was 1.4. Okay? So one of the given values. So 8.99, well, actually, let me not take any shortcuts. ID average, multiply by the safety factor. So 8.993 milliamps multiplied by 1.4. Which gives us 12.59 milliamps DC. Why is this guy here important? This guy here is going to help us decide which diode by comparing it to the IO. And so in your notes, where you're writing all this down, write that in as a reminder. It will help you a few months from now. Okay. Yeah, we'll be repeating it anyway. And PIV safe. PIV safe is just basically PIV multiplied by the safety factor. So PIV multiplied by the safety factor. So PIV was 28.28 volts, or multiply by 1.4, or add 40%. 28.28 multiplied by 1.4. 39.59. 39.59 volts. So this guy here will be important as well. It's not always going to be under 50, in case you're wondering. These ones are so far. We're going to take this guy here and we're going to go to the spec sheets and compare this to VRRM. Any questions so far? Am I going too quick? Am I going too slow?
Okay, I have a question. Okay,
Yes.
so ID average safe, and okay, so the units at the end is milliamps DC.
Yes.
How do I know that it's milliamps DC at this point? Well, like I don't like I get like what that means, but I don't know how we just knew that it was milliamps DC.
Okay, is it the milliamps or the DC you're having an issue with?
It's the DC.
The DC. So remember when
Is
I
it because
said
it's
average
yeah?
is the same thing as saying DC. Average
Oh
and DC
yeah,
mean the
that's
same thing.
right. Yeah, okay. Yeah, that's right. All right.
So we're good?
Yeah, okay, yeah, I remember. Okay. Yeah,
Yeah.
right. Yeah.
That's minor stuff. If that's your sticky point, we're doing well. Okay, so diode number. To choose a diode, we're going to go to our spec sheets right over here. We went through this morning a little bit, and it's basically two rows we have to look at, the VRRM and the IO. All of these diodes here are good for 1 amp. I mean, how many milliamps are we at here? We're at 12.59 milliamps. As far as the current goes, the IO, it's fine. Now we have to look at VRRM. We have 39.59. So if we choose this guy here, which is the 1N4001, it's good till 50, right? And again, the amperage, 1 amp. So we can use the 1N4001. So 1N4001, which is good for 1 amp and has a VRRM of 50 volts. Is everyone okay with this?
Yeah.
No, can you go over that again, please?
Claudio.
Yeah. Yes,
So
Evan.
when I was calculating IR average, I used the calculated function, the calculated number for RB instead
Yeah.
of the resistor one.
Yeah, you still would have gotten the same answer.
I
Right?
did. I got the same answer.
Yeah, just that what's going to be wrong is the next section, the justification, because your values won't be right.
Yeah.
So you're not
Okay.
going to burn anything, but your numbers here are going to be wrong. Okay, so make a note of that. Just make sure that your RB here is whatever we're actually going to use when we assemble it.
I have a saved one and I have the corrected one.
Okay, perfect. And Eric, you were saying this part here?
Yeah, I'm still. Can you just show?
So you see these two variables here, ID average safe and PIV safe.
Yeah. Okay.
Right? So ID average safe, we're going to compare it to IO of the spec sheet.
Yeah.
And PIV safe, we're going to compare it to VRRM. Both of these values here, Eric,
Yeah.
if we go to the spec sheets, are right here. We have our VRRM. Let me erase some of this and start from scratch. Maybe
Yeah.
it's,
Yeah. Thanks. And can you zoom in a little bit, please?
I could. Okay. All right. So what we're using here is, see this VRRM? This whole row is VRRM.
Okay.
This whole row here is IO.
Oh, okay. All right. Okay.
So let's just go back here. Like I said, IO, VRRM. We're comparing this value here, ID average safe, what we calculated with IO. What we calculated for PIV safe, we're going to compare that to VRRM.
Okay.
So we're good with the amperage because it's all of these diodes are good for 1 amp. We're nowhere near 1 amp.
Oh, okay.
And since we're at 39 point whatever volts, well, that's under 50, so we can use a 1N4001.
Oh, okay. All right. That's pretty cool. All right. Sure. Okay. That's cool.
Okay, so that's why we put 4001, which is good for 1 amp. So here you put in the specs of the selected diode.
Oh, okay.
1 amp, 50 volts. Now at the bottom here, there are two things we have to justify. We have to justify our choice based on the current and the voltage calculations versus the spec sheet. So we can start with volts. Okay, so how do we justify volts? We can say that PIV safe, we calculated to be 39.59 volts is less than VRRM of 50 volts. So in essence, what we're doing here is we're saying that PIV safe, which we calculated to be 39.59 volts, is less than, so you're making a comparison. I'm just going to underline and bold this part here. And then less than what? Less than what it's the specs are.
Yeah, less than the 50. Okay,
Right.
all right.
But I'm putting, what is that 50? That 50 is VRRM. So this is spec sheet. This is
Okay.
calculated.
All right, I think I get this now. All right, okay.
Good.
Yeah, all right, okay.
So now we're looking at the amperage. How do we justify the amperage? So it's kind of the same thing. I'm just, instead of, here I went less. So now what I'm going to do, I'm just going to change the wording around a little bit. I'm going to say IO, not IP, but IO of 1 amp is greater than ID average safe of 12.59 milliamps.
Okay.
What happened there? 12. My numlock, is that it? 12.59 milliamps. So we've got the IO, and we got the 1 amp. Well, actually, let me just stick with the same colors here. We got the IO. This is the spec sheet of 1 amp. We're going to compare it. So is greater than. And then greater than what? Than what I calculated. So the actual current that's going to go through, which is ID average safe of 12.59. Okay, so we're justifying the voltage. We're justifying the amperage. How are we with that? Good.
Yeah, it's good.
Okay. Anyone need more time to copy this? We're good to go. Just gonna double check that I'm recording it for you. Yeah, okay, so it's good. Christy, we're good? Or do you
Yeah.
need more time? You're
No,
good?
no, I'm good.
All right. So all we've done now on that previous page, page 3, is we've decided which diodes to use. Okay, we were using that RB basically to see what the amperage and voltage that they were going to be subjected to. And based on that, we'll look at the spec sheets. We selected them. That's done. Now we're looking at this, the Zener. We have to select which Zener we're using from the spec sheets and justify its use as well. So VZ, we're building a power supply that'll be good for, so 12 volts. Where do I get the PZ nom?
Isn't it always 1?
Always 1.
Yes, it is. So let's go back to this page right over here. I'm going to clean this up for you as well. So PZ nom, PZ. So this is what we're going to be using. PZ nom, this is for your Zener diode. PZ nom, all of the ones that we have in our kit are good for 1 watt. And what we're going to be focusing on is this this column right here where it says VZ. VZ is basically equal to EO, which is equal to EZ. Okay. So let's go back. PZ nom, 1 watt. So from the spec sheets, as it says right there. Do you remember what we're using here to find this guy? The I. It would be maybe a good idea to group these together because basically you're going to get the I by using the triangle, pi or PEI. Okay, so what am I looking for? I'm looking for the I. How do I get the I? It's P over E. So P divided by E. The only P and E that I have here is my PZ nom of 1 watt. So 1 watt, and I'm going to divide that by the only voltage I have here, which is 12 volts.
Sorry, can you explain, because I forget now, can you explain it again how we got the 12 volts?
Yeah, the 12 volts is basically a given value. We're building
Yeah.
a power supply And the power supply, if we look at here at EO, which
Oh, yeah,
is right
okay.
here, it's right here, 12 volts.
Oh yeah, okay. So could I just say for all future reference that VZ equals EO?
Yes.
All right, I'm writing that down on my. All right.
Well, you're gonna write it down at the bottom of the page, right over here. Okay, you can write it down elsewhere as well if you want, but we're gonna get to it. Okay, so 1 watt divided by 12, so 1 divided by 12 is equal to 83.33. So 83.333. What are we looking at? Milliamps. Okay. So that's the maximum. We're good to go?
Yeah, just writing this down. Just erasing some stuff.
Yeah.
Fixing it.
So
here.
we're looking at this guy here. This guy here is IZ. That is the max. Anything beyond that, what's going to happen? We're going to exceed 1 watt. Okay? It's probably going to start smoking. So not only do we have to worry about the max, but we have to worry about the happy, which is the minimum value. Because if we're below the minimum value, it's not going to maintain that voltage. Okay? So here what we're going to do is we're going to take the IZ max and we're going to multiply it by 0.1, which is basically 10%. So just basically moving the decimal point by 1 to the left, so 8.333 milliamps. That's your IZ happy.
Claudio,
So it means that we have a minimum of 8.33 milliamps. If we have less than this, it's not going to work. It's not going to maintain the 12 volts. And we had an IL of, what was the IL? Who can give me that value again? 50 milliamps?
15.
Yeah.
15, 1.5?
Yeah.
Okay. Okay, so we have the load that needs 15 milliamps. We have the Zener that needs a minimum of 8.33 milliamp. Otherwise, it can't maintain the 12 volts across the load. Okay, and then eventually, with that, we're going to get the IT.
Oh wait. Can you explain again? Just so the IL it needs to be 15 because what? Sorry, that you went a little
Well,
fast there.
the IL is a given value as well.
Oh yeah, that's right. Okay.
So the IL is right here, 15 milliamps.
So that's the minimum amount of juice to run the system.
That's the minimum amount of current that the load needs. Well,
The
that is the
load
current.
needs,
That's
okay.
the current that the load needs.
All
So
right,
an example,
okay.
if we're building this to charge your phone, well, it's going to take 15 milliamps to charge your phone.
Okay, a minimum. All right. Okay, cool.
So IL is a given value, which is 15 milliamps. And IT was a bit tricky. Actually, it wasn't IT, it was PZ. IT is not that tricky. IT is basically the current right over here. Well, that's IT. So the current going through this resistor here, which is going to be distributed to the load and to the Zener. Well, the minimum IT would be IL plus IZ. That's the current that I need. Renaud, it looks like you're having a really good time there. Good? Any questions, Renaud? So 50 milliamps plus 8.333 milliamps. So we're looking at 2333. 23.333
Million.
milliamps.
Yeah, milliamps. Okay.
So that's what we need up here. 23.33. Remember, that's a minimum value that we need. Okay. Anything less than that, IZ is not going to get the min. And if IZ doesn't get the min, it can't maintain the 12 volts across its load. PZ safe. So what is P? If we look at the triangle here, P is what? I times E. So we have an E times an I. But which E and which I? Well, we're looking at the power across the zener. Power across the zener, you want the voltage across the zener, which is what? EZ, which is VZ, which is EO, which is, let me just write it down as EO first. And multiply by I what? So you would think IZ. What was the reason for it not being IZ yesterday? Who can remember? Remember this device here. This is not hardwired. What is this load?
It's
This
whatever
load is
you're-
whatever it is you're charging.
Yeah.
Is it always connected? No. If I disconnect this, well, I have an IT here of 23.33. It's being distributed amongst these two. If I disconnect the load, well, where's this 23.33 going to go? It's going to go through the zener. Okay. So for the power across the zener, instead of just using the IZ, I'm going to be using the IT. So it has to be able to sustain that. This guy here is IT. And then we're going to multiply by the safety factor. So EO is 12 volts. We're going to multiply that by 23.333 milliamps, and then we're going to multiply that by 1.4. That multiply by 12 and multiply by 1.4. So 392. Correct me if I'm wrong.
Yeah, that's what I got to.
Okay. Milliamps, negative, milliwatts. What can this not exceed?
1.
1 watt. This guy here has to be less than PZ nom of 1 watt. Okay.
What happens if it does exceed a watt? Like
Well, it's going to get hot. It's going to eventually burn.
it's gonna blow up.
It's not going to blow.
You're gonna take out the whole block.
No.
All right.
If you touch it, it'll burn your finger.
Okay.
If you inhale it, you might get lung cancer. But aside from that, you're good. You don't want to be breathing any of this stuff that's smoking. No semiconductors. It's really not good for you.
Yeah.
So Zener diode number. Eric, how do I choose a Zener diode number?
Okay, so we need to let's see. We need to compare the PZ safe and the is it the IT to the table?
Well, we have to go to the table.
Yeah.
We
okay.
we know that this Zener has to maintain 12 volts. So if we go
Yeah.
to the table, go right here. Where's our 12 volts? We can zoom in here. Our 12 volts is right here.
Okay, yeah.
So we need a 4742. This is what we need to purchase, and this is what we need to install. Okay?
Yeah.
A little bit, but that's a 4742. Okay? So now, let's go back here. What are we going to use? We're going to use a 1N 4742,
Okay.
which is made for or made to maintain or regulate the voltage of 12. And PZ nom 1 watt for everything on that page.
Okay.
So the justification here, there's one that's very easy. How do we justify the volts? Well, it's basically what we just did. We went to the spec sheet and we said that, well, we went to the VZ column and we said, well, VZ is what? Well, VZ is whatever the voltage across the zener is, which is whatever the voltage across the load is, which is a given value, which is 12 volts. That's it. Okay. And now we have to justify the power. So how do we justify power? Well, the PZ safe of 392 milliwatts is less than PZ nom of 1 watt. So again, PZ safe calculated. What was the value we calculated? 392 milliwatt. We make a comparison. Is it greater than or less than the PZ nom in the spec sheet? And the PZ nom value is 1 watt. Okay.
Okay. So in a sense, we need to do all this math so that we get the PZ safe so we can do the justification, but not necessarily so we can pick the Zener diode number.
Not for the power, no. The power is what's justifying it. The voltage is justifying it, but I mean, there's no math involved here. I'm telling you that you have to build a power supply that's good for 12. Automatically, the Zener is going to be 12.
Yeah. Okay. All right. So yeah. Okay. So all right. Okay.
Good?
Yep.
All right. So RS max. What is RS max? I'm going to write this down with a pen here. RS max, let's go back to the diagram here. I'm looking for the voltage here. Okay. So let me redraw that in a way where maybe you can trigger what we did yesterday for the Zener diodes. Okay, we had an RS there. We had our Zener here. I'm purposely putting a DC voltage here just so that you remember what we did yesterday for the Zener diode. Okay, this is still the RL. So this is the RS. This is the work for the RS. Okay. Now instead of having DC here, in reality we have a waveform, which is actually coming from the capacitor, which gives us a ripple. Okay. So what we're going to use here in terms of voltage is the peak voltage. So what this is, what we're going to write down here is E peak. Okay. But we want the voltage across here. What is the voltage here? Well, it's not peak. Why is it not peak? Because there's a loop here. We have the voltage here. We're going to use the peak. But we also know that we have 12 volts across the Zener diode right here. Okay. So the voltage here is what? The voltage here is E peak minus EO. And since we're looking for the resistor value, what we're going to do here is we're going to put the IT of 23 over IT. So we figured out IT before. IT was the current going through here. So if we have current IT and we have the voltage here, which we're going to get by subtracting EO from E peak, and that should give us a resistor value. So the E peak was 28.28 minus 12, 16.28. And I'm not writing everything out because I don't have much room here. So volts, and the amperage, I forget. What was the amperage? It was 23.333. 23.333 milli. Okay, so 16.28 divided by 23.333 is 697.7. 697.72 was it? 72 ohm. Okay. So now this resistance here, if I were to put this in the circuit, I would get the current I need here, which was 15 milliamp, and I get the IZ min of 8.33. Do you understand that if I choose one in my kit that is larger than this, then my current IT will be lower. If my current IT will be lower and RL still takes 15 milliamp, well, I'm gonna be left with less than 8.33 for my Zener. So what I'm gonna do from the kit, I'm gonna choose one that is of a lesser value. Let me draw that here, which is the 470 ohm resistor. Are we good with this? Questions?
Yeah, I'm not really good with this.
Okay, so I'm going to repeat it.
Yeah.
Okay. So do you recognize this circuit here? It's
Yeah.
basically the same as this part here.
Yeah, okay. I can see that part. Yeah.
So the E peak would be here. What I
Okay.
want is the voltage here. The reason I want the voltage here is because I want to get what is this resistor value? We don't know what it is. We have to calculate it.
Okay.
So if I have the voltage here, using Kirchhoff minus the voltage here, I'm going to get the voltage here. That formula is basically here. E peak minus EO. E peak minus EO will give me the voltage here, 16.28. So I have 16.28 volts across here. Now I want the resistor value. Well, R is equal to E over I. Well, that IT, I've also calculated here, 23.33 milliamp. So I have the two variables that I need to get the resistor value. I have the voltage across here, and I have the current across here. This is the voltage, this is the current. That gives me 697 ohm. I don't have a 697 ohm in my kit. What I do have in my kit that comes close to this is a 470, and I have a 1K.
Okay.
If I use a 1K, if I just use Ohm's law, right over here, just please pay attention, okay? The voltage across that RS is 16.28. If I divide this by 1K, if I were to choose the 1K, what's my current now? It'd be 16.28 milli. Okay, are you with me, Eric? And everyone else?
Yeah.
How much does the RL branch need? It needs 15.
So it's too much.
Well, it needs 15. What am I left with if I subtract 15 from 16? I'm left with 1 milliamp, sorry.
Yeah.
Well, I need 8.33 min for the Zener, which means that if I increase this resistor value from 697 to 1K, I don't have enough current to supply the Zener diode. So it's not going to work. I can't use a larger one. I have to use a smaller value resistor. So I move on to 470. That will assure me that I have enough current for the Zener.
Okay.
Now here, the PRS nom, these are nominal values, 0.5 watt, 1 watt, 3 watt. We can't select it yet because we haven't done the wattage, which is going to be down here. Okay? IT new. How do I get IT new? Well, look, I'm using Ohm's law. How do we get IT new? Well, I'm looking at E over R. Well, where is IT new? IT is here. Why is it new? Because I'm not using a 697 ohm resistor. I'm using a 470. So that's going to change IT. Therefore, it'll be called IT new. So what is my voltage there? Well, my voltage there is the voltage that I wrote down here, E peak minus EO. So actually, let me just clean this up a little bit and take this. I'm going to be more specific with what this is. What is the E? Look, for now, I can even call this ERS, okay? But what is ERS? ERS is basically E peak minus EO. Minus the EO, which I've already worked out. Right up here, 16.28. Oops, 16.28 volts. Okay, divided by the resistor value. What resistor value? RS final.
So 470? That's the 470?
Yes, RS final, RS final. Okay, I'm just abbreviating the final, FIN, and 470. So since we didn't have a 697, we went to 470. So 16.28 divided by 470 is equal to 34.638. 34.638 milliamps. Excuse the handwriting there. Okay, that's the new current. Okay. So if I just maybe change colors here, just to bring this home, this 34.63 is my new current going in through here. So now instead of just 23, I have 34 available. So one last thing to do is figure out, well, I have the resistor value, but based on the amount of current going through, how much power will it dissipate? And I want to make sure I choose the right wattage. So this again is also the voltage ERS. And what is ERS? It's E peak minus EO. Okay. And I'm going to morph this a little bit into a combined. Just going to underline it like this. Okay. So ERS, the bottom here, I'm looking at let's erase that. So I have 16.28. But I don't want to take a shortcut. I'm just going to put that in brackets for now. I'm going to multiply by IT new. And I'm going to multiply by the safety factor. So if I fill these values in, I have 16.28. I'm going to multiply by IT new, which is 34.638 milliamp. And I'm going to multiply by the safety factor, which is 1.4, which will give me a grand total of times 16.28 times 1.4, 789.476 milliwatts. So this guy here decides the wattage here. So I can't use half a watt because I have 789 milliwatts, which is greater than half a watt. I'm going to use a 1 watt. So those two bits of information together will help me fill in the box at the bottom here. What is my RS final? The resistance value of 470 ohm. And what is the nominal wattage? Well, based on 789, I'm going to purchase a 1 watt resistor. And then I have to justify it. So what am I justifying? That 789 is less than 1 watt. And also the 470 ohm is less than the 697. Okay, so let me write that down. We're going to justify the power. So P RS nom of 1 watt is greater than PRS safe 789.476 of 789.476 milliwatts. Comparing the spec sheet value of 1 watt to the calculated value of 789 milliwatt. Okay. This is the comparison. The comparison always has to be true. So that's for power, and now for not wattage, but power is wattage. We're looking at resistor value. So the way we justify that is that our RS final of 470 ohm is less than RS max of, what was it? 697.72. 697.72 ohms. Therefore, there is enough current for both the load and the zener. All right, how are we with this? Good?
Not bad. It's more practice will help, but not bad.
Yeah, it is. I mean, this is just the second one, right? So the first one yesterday is purely for notes. This one here, you know, you're going to get the hang of it. It's basically all the same calculations over and over again. At first, when you first learn something new, it's like there's a lot of formulas, but it's very sequential. I mean, everything that's being asked is being asked in a certain order.